Hello everyone, welcome to the third lecture series of our lectures, that is sensor and instrumentation, that is measurement of force and pressure. In last lecture we go through the measurement of displacement. Now in this time we focus on the parameter, that is force and the pressure. Now let's see what is the difference between a force and a pressure, or both parameters are literally depending upon each other with some values. Like force is external influence, that is push and pull, that changes or tends the change of the state of rest or the motion of a body. So when force is applied to a free body, it gives the body an acceleration in a direction of the force. Thus, we can define force as a vector value. Now, Newton has found that acceleration is proportional to the acting force and inversely proportional to the property of the body called mass. So, which is a scalar value. So, that is acceleration is equals to force upon mass, or force is equals to mass into acceleration. Now, what is pressure? Pressure is the force exerted per unit. Suppose it is upon an area, how much force you have applied, it will give out the value of pressure. So, whenever pressure is measured, it requires the measurement of force. So, it could be said that force is measured when dealing with solid, while pressure while dealing with the fluids or liquid or gases. So, that is something force is considered when action is applied to a spot, and pressure is measured when force is distributed over a relatively large area. So, pressure is equals to force upon area. So, if it is if area is finite, then it can be say, or 1 meter square, then you can say that pressure force is a equal quantity. Then what are the force sensors available? So force sensor can be divided into two types, like it should be a quantitative format or in a qualitative format. So quantitative sensor actually measure the force and represent its value in terms of electrical signal. Example of these sensors are strain gauge or load cells. Now, qualitative sensors are threshold devices that are not concerned with the good fidelity or representation of the force value. Their function is merely to indicate whether the sufficient strong force is applied or not. That is, the output signal indicates when the force magnitude exceed or predetermine the threshold level. An example of these detectors are, that is a spring-loaded force sensor with LVDT. And this is a force sensor incorporating a pressure value. So, this is something, these are the bellows. Okay, it is a kind of a primary sensing element. So, whenever you applied a force, there is some output is coming out in terms of a displacement or pressure. Okay. So, the various method of sensing force can be categorized as follows: by balancing the unknown force against the gravitational force of the standard mass, by measuring the acceleration of the known mass to which the force is applied, by balancing the force against an electromagnetically developed force, by converting the force into a fluid pressure and measuring the pressure, by measuring the strain produced in an elastic member by an unknown force. So, these are the methods that you can use to measure the force. Now, how force is related to strain? Force applied produces a stress on the element. If it is an elastic member, obviously, then stress is equals to force upon area. It is given by sigma. According to Hooke's law, that is longevity is equals to, that E is a Young modulus. So longevity is equals to stress upon Young modulus principle. Young modulus constant, and epsilon is equals to F upon A into E, that is force upon area into Young modulus. You have, I think, uses Young modulus as Y, that is a Young modulus constant. So it is like E is equals to, that is strain is equals to stress upon Young modulus principle, and or you can say stress is equals to force upon area. It is force upon area into Y. Okay, so how the strain is measured? So strain is a deformation of a physical body under the action of the applied force. Strain gauge is a resistive elastic sensor whose resistance is a functional of a applied strain, that is unit deformation. Since all the materials apply to cause deformation, some force must be applied to cause deformation. Hence, resistance can be related to the applied force. That relationship is generally called the piezoresistive effect. It works on the principle that the electric resistance of a conductor changes with the strain, that is elongation or compression. When force is applied to a mechanical when force is applied to the mechanical member like a cantilever beam, load cell body or diaphragm, it undergoes strain. This strain is transferred to the strain gauge and which changes its resistance. So delta R, that is change in the resistance, is equals to gauge factor into resistance into the strain. So where R is equals to initial resistance, delta R is a change in the resistance, GF is the gauge factor, and sensitivity of the gauge typically is 2, and epsilon is the strain. So strain is equals to delta L by L. The fundamental parameter of the strain gauge is its sensitivity to strain expressed quantitatively as a gauge factor. So gauge factor is the ratio of the fractional change in a electrical resistance to the fractional change in a change in length or strain. So GF is equals to delta R by R upon delta L by L or delta R by R by epsilon. So if you go through the construction, this is the metallic grid pattern of a strain gauge. If you see, strain gauge is a small sensing device where resistance changes with the strain. So base carrier, there is a base carrier, backing a material, thin, flexible, insulating material, example polyamide or epoxy resin. Then we have, it provides a support and ensure bonding with the specimen. We have grid, that is a resistive wire. This is a grids. So fine conductor wire or metallic foil arranged in a zigzag serpentine pattern. Common material, constantine, nichrome or foil alloys. The grid length determines the sensitivity. Then we have a leads, electric connection, copper leads or soldered to the ends of the grid to connect with the Wheatstone grid circuit. Protective coating, resin or plastic coating applied for the protection against humidity, dust and the mechanical damage. So if we go through the mechanical side, how the strain gauge has been proceed to the next part like a signal conditioning circuit. So we use the Wheatstone bridge. In Wheatstone bridge, we connected a strain gauge in a one arm, or you can put a strain gauge in all the arms depending upon which how many strain gauge have been connected. We classified the circuitry as a quarter bridge, half bridge and full bridge. Quarter bridge, there is a single active strain arm. There is a half bridge, that is 2 active strain arm. Then we have a full bridge, that is 4 active strain arm. So if we have a full bridge, then we have a, this is the formula, that is V0 is equals to R3 upon R4 plus R3 minus R2 upon R1 plus R2. This is R2 into external voltage. Now, external voltage is the bridge excitation voltage. It can be 5 to 10 volt DC usually. So, V0 is equals to delta R by R into Vx upon 4. So, if you see delta R by R is what? If we see that delta R by R is what? This is delta R by R. If you see from here, the formula GF into epsilon is equals to delta R by R. And if we put this formula here in this value, it can be like that V0 is equals to GF upon 4 into epsilon into Vex, that is external voltage upon 4. So this is the formula if in terms of the gauge factor. Now, what are the advantages of strain gauges? High accuracy, sensitivity, compact and lightweight, can measure very small strain, that is micro strain, wide frequency response, good for dynamic measurement, easily integrated into a load cell, torque sensor, pressure transducer and relatively low cost. What are the disadvantages? Output signal is very small, requires stable amplifier, sensitive to temperature variation, causing drift, requires careful surface preparation and bonding, limited strains range, only elastic region, prone to creep and hysteresis, adhesive and material effect, fragile and easily damaged if mishandled. What are the applications? Force and weight measurement, load cell in weigh bridge, packaging machines, pressures, hydraulic and pipeline pressure sensors, torque and power for engine, turbine, gearbox monitoring, stress and fatigue, bridges, aircraft wings, civil structures, robotics, gripper force control, automotive crash test, brakes, suspension load, medical, prosthetic, blood pressure sensors, aerospace and defense, aircraft, structural testing, and missiles. Now, move to the pressure part. Now, for pressure, we have a piezoelectricity sensor. Now, piezoelectricity is what? Piezoelectricity is the charge created across a certain material when mechanical stress is applied. So, if you, I already told you, the piezoelectric sensors are the inverse transducers, or we can use it is a active transducer or passive sensors. So, piezoelectricity is whenever you have applied a force or stress to these material, the charge has been created across these materials. Piezoelectric pressure sensor exploit this effect by measuring the voltage across a piezoelectric element generated by the applied pressure. They are very robust and are used in a wide range of industrial application. Now, if we go through the construction, the piezoelectric effect requires material with a specific asymmetric in a crystal structure. This includes some natural crystals such as quartz or tourmaline. A special formulated ceramics can be created with a suitable polarization to make them piezoelectric. These ceramics have higher sensitivity than natural crystal. A useful output can be generated with a little as 0.1% deformation. Because of the piezoelectric materials are rigid, only a very small deflection of a material is required to get usable output signal. This makes the sensor very robust and tolerant of overpressure condition. It also means they respond rapidly to the changes in the pressure. The pressure sensor can be affected by any external force on the piezoelectric element, for example, by force caused by acceleration or noise. Microsensors can be constructed using a thin films. Zinc oxide was one of the first material used. This has largely been replaced by the ceramics made from the materials such as zirconate and titanate because of their larger piezoelectric effect. Now, this is a piezoelectric sensor. If you see by the construction, this is how the force applied. These are piezoelectric sensor. The electrodes are there. The thickness is there, and the output voltage has been calculated. If you cut the piezoelectric sensor, this is how it is shown. So, the piezoelectric pressure sensors are often constructed in a threaded tube as shown in the diagram. And to make it easy to mount them in a equipment where the pressure has to be monitored, care is needed when installing these because over tightening can affect the output sensitivity. In some of the typical application of the piezoelectric sensors, they may be exposed to thermal shocks, a sudden change in a temperature caused by the either radiant heat or the flow of the hot gases or the liquid past of the sensor. This can cause changes in the output due to the heating of the crystal, the diaphragm of the casing of the sensor. Note that this is not the same as the static temperature sensitivity of the sensor. The effect of the thermal shock can be minimized by the design of the enclosure and the mounting of the sensor. So, you see the piezoelectric sensors are a dynamic sensor. So, if you apply a static force on it, the output will be a zero. So, that force should be in a dynamic nature. Dynamic means it will be changing with respect to time, not it should be a constant force. So, if it will be a constant force, then the output will be a 0 volt. Now, let's go to the working principle. Unlike the piezoresistive and the capacitive transducer, piezoelectric sensors element require no external voltage or the current source. They generate output signal directly from the applied state. The output from the piezoelectric element is a charge proportional to the pressure. Detecting this require a charge amplifier to convert the signal to a voltage. Some piezoelectric pressure sensors include an internal charge amplifier to simplify the electric interface by providing a voltage input. Now, this requires power to be supplied to a sensor. Now, the input to the piezoelectric sensor is a mechanical stress or force applied on the piezoelectric crystal. Stress causes strain in a crystal lattice leading to electric charge generation due to piezoelectric effect. Output is an electric charge that is Q, or the voltage proportional to the applied force. So the charge output will be like Q is equals to dF, where D is the piezoelectric charge constant, which is given by coulombs per Newton. So Q is equals to D into F. Now if you remember the capacitor value, that is Q is equals to CV. So basically, since it is a pressure, it is like a capacitor where we have a charge at the upper and in the upper layer and the lower layer, and in between there is a material, there is a dielectric material. So it is something like a capacitor. It behaves like a capacitor. So in a capacitor, you see Q is equals to C into V. So if we Q is equals to here C in the piezoelectric charge constant into F, and if we replace CV into C is the capacitance and V is the voltage, the external voltage. C into V is equals to the voltage generator, D into F. Then the voltage generated will be equals to D into F upon C. Here it is that whatever I give you, this is the formula of the output voltage that is generated. Okay, now it is it can be affected like if we further go down, then C is equals to what? C is equals to epsilon A by D. And if you put here the value like epsilon A by D, then V is equals to what? Let's see D as the thickness, because D is the length, the distance between the the length of the plates. So the distance between the plates. So epsilon A by D, let's take it is a T, then put it here, then we have a D is equals to D into F upon epsilon into A into T. So the final value, if you know the distance, the thickness of the material, the area of the material, you can go through that. Now the working principle: when a force is applied to the piezoelectric material, an electric charge is generated across the faces of the crystal. This can be measured at a voltage proportional to the pressure. You have to see the diagram. There is also an inverse piezoelectric effect when applying a voltage to the material will cause it to the change in the shape. A given static force result in a corresponding charge across the sensor. However, they will leak away over time due to the imperfect insulation, the internal sensor resistance, attached electronics, etc. As a result, piezoelectric sensors are not normally suitable for measuring static pressure. As I already told you, it is not usually suitable for measuring a static pressure. The output signal will generally drop to zero even in the presence of the constant pressure. They, however, sensitive to the dynamic change in the pressure across a wide range of the frequency and pressure. This dynamic sensitivity measure, they are good at measuring small changes in the pressure even in a very high pressure environment. Now, what are the advantages and disadvantages? One of the main advantages of piezoelectric pressure sensor is their ruggedness. This makes them suitable for use in a variety of harsh environments. Apart from the associated electronics, piezoelectric sensors can be used at high temperature. Some material will work up to 1000 degrees centigrade. The sensitivity may changes with temperature, but this can minimize by appropriate choice of material. The output signal is generated by the piezoelectric element itself, so they are inherently low power device. The sensing element itself is insensitive to electromagnetic interference and radiation. The charge amplifier and the electronics need to be carefully designed and positioned as close as possible to the sensor to reduce noise and other signal errors. Piezoelectric sensor can be easily made using an inexpensive material, for example quartz or tourmaline. So they can provide a low-cost solution for industrial pressure measurement. Want to learn more about the other core technology used in a pressure sensor? Now, robustness. What should be the application? Robustness, high frequency and rapid response time for piezoelectric pressure sensors means they can use in a wide range of industrial and aerospace application where they can expose to high temperature and pressure. They are often used for measuring dynamic pressure, for example, turbulence, blast, and engine combustion. They all require fast response, ruggedness, and a wide range of operation. Their sensitivity and low power consumption also make them useful for some medical application. For example, a thin film plastic sensor can be attached to the skin and used for real-time monitoring for the arterial pulse. So that is for now. So this is how we can done. And if we see that what are the application that when you go to the force sensor and when you go to the pressure sensor, this depends mainly on the applications. You see, the strain gauge has been strain gauge and the piezoelectric sensors are those which can be used in the industry. But depending upon what you are wanting, if you want higher sensitivity, then you especially go for the piezoelectric sensor rather than the strain gauge sensor. Then again, the piezoelectric sensors, the signal conditioning circuit are very much better as compared to the strain gauge transducer. But as you know, strain gauge transducer is mostly the signal conditioning circuit is mostly a Wheatstone bridge, which is a very cheap, and the accuracy and the resolution of the Wheatstone bridge is very high because it uses the null kind of deflection, because if there is a balancing condition is there, so precision is very high in a Wheatstone bridge as compared to the signal conditioning circuit we used in a piezoelectric sensor. So there is a difference between a piezoelectric there is a difference between the application, obviously, why you are using, whether you want how much the range you are using the inputs, what are the ranges, what are the environmental condition, what are the parameters you are focusing, what are the material you are focusing. So these all are the conditions that requires to whether you can go to the pressure sensors or whether you can go to the force sensor, and whether you can go for the strain gauge or the piezoelectric sensor. So that is all for today. Thank you so much.